Are you ready?
I'm ready.
Okay.
Yeah.
Okay, let's get started. It is my pleasure to introduce Ellie Grigsby, who's a professor at Boston College. She did her PhD at Berkeley and was an NSF postdoctoral fellow at Columbia. She's won many awards for her research, including the PCAS Award. She's a very well-known person in the mathematics community and was a director at ICERM for a while. Not anymore, or
Not
still
anymore, yeah.
not
Well,
anymore.
deputy director.
Deputy director. When we invited her to come here and give a talk, Thomas and I actually decided, it was her talk that inspired us to build the whole workshop around her talk. No pressure or anything for your talk, but thank you for coming here. Let's welcome her.
Thank you very much. It's actually been a real pleasure to be here the last couple of days. I found that the diversity of subjects and how interesting they all are has just been really a treat for me. This is going to be a talk about optimization and generalization in modern parameterized function classes used for learning problems. Let me just start by saying I think that we don't really understand optimization in modern parameterized function classes. There's almost nothing that we understand somehow, and I think
it's hard.
we understand that it's hard, and I think that the way that I explain this, at least to myself, is that the optimization algorithm that we use in learning problems are largely based on gradient descent. And gradient descent is fundamentally a geometric process. But we don't really understand the geometry of these modern parameterized function classes. So we have these old function classes from which we base our intuition, classes like polynomial classes. And in those cases, we kind of understand very well that there's a one-to-one correspondence between parameters and functions. And moreover, lower complexity classes in there are measure zero. But in modern parameterized function classes, if you remember nothing else, I think I'd like you to remember this, that in modern parameterized classes, I think this is very much not the case. Okay, I like to put my references right up front, just in case anybody wants to ask me for my slides. You don't have to go hunting through. So there are some expository references, there are some of the research references. Okay, so I'm going to start from the very beginning. Hopefully this is not too boring to experts, but I really want to, because I know that this is a diverse crowd, I want to make sure that I bring everybody along. Okay, so I'll start by motivating the problem. So what are we doing when we're doing learning, supervised learning? Let's say a curve fitting task, a regression task. Well, we start with some finite labeled data set, input-output pairs inside of some large dimensional spaces. And then we choose a big bag of functions. And we're trying to pick the function from the bag that best fits the data or best predicts the labels from the inputs. Okay, so we're trying to learn the optimal function, allowing us to predict the outputs from the inputs. And we typically do this by doing, as I said, gradient descent on some empirical loss function, so just on this particular batch of data. But of course, as we know, this batch of data is typically sampled from some probability distribution that we don't really know except via the samples. And so really the task is not to fit these particular data points, but to generalize well to unseen data. Okay, so let me just give like a really simple example of the classical intuition here. So here we have one period of the sine function and then some data points whose labels have been perturbed by some Gaussian noise. Okay, and now if we pick like one of these classical function classes, polynomial function classes, and we look at different degrees of polynomials, so different number of parameters for this class of functions. The complexity of the class that we choose measures somehow more than the actual optimization procedure. If we restrict to degree 2 polynomials, we're going to be prone to underfitting. If we restrict to degree 15 polynomials, or if we make our bag of functions be degree 15 polynomials, we're going to terribly overfit our data. So this is kind of one of the first slides that you would show in an undergraduate machine learning class. So this slide appeared in Yoav's talk. So in the sort of modern learning regime, we have these, so somehow here is the standard bias variance curve, but when we go to this heavily overparameterized regime, somehow all of a sudden we start doing better on test data for some reason. So the takeaway here is that these modern high complexity function classes that we are actually using manage to fit without overfitting. And what this is saying to me is that the number of parameters, which is a global measure of complexity for your function class, is just inadequate. It's not going to be able to capture anything that we really want to understand about optimization. So the point of view that I'd like to promote is that modern classes are very inhomogeneous with respect to complexity. And it'd be awesome to try to understand local versions of complexity that play well with gradient descent, that we can kind of understand play well with gradient descent. Did you have a question?
Yeah, so just let me confirm. So in the figure for the x-axis, the capacity of the edge is actually the number of parameters?
Yeah, I think that's what that's supposed to measure, but it's some kind of global measure of capacity of the class. And typically what people take as that capacity is the number of parameters.
I guess maybe what Rachel is getting at is that if you measure your capacity by other metrics, then the double descent vanishes.
Yes, yes. And I think the point is that that number of parameters is definitely not a good measure. Okay. So yeah, I think that this is sort of the current conventional wisdom about what's sort of going on, which is that actually you have high dimensional critical sets for your loss landscape, for your empirical loss landscape. And for some reason, the dynamics of gradient descent is pulling you toward regions that are higher dimensional. So here's like a toy example of that, where you have this two-dimensional zero set along with this one-dimensional zero set. And the idea would be that for some reason, gradient descent is pulling you towards this flatter region. So this is the sort of one model of this implicit bias that Yoav mentioned. Okay, so here's my proposed mantra that again, maybe if you remember nothing else from my talk, remember this, that modern function classes are inhomogeneous in terms of complexity, and this impacts gradient-based optimization algorithms. And the more detailed version is that actually there are high-dimensional parameter space symmetries. So in other words, what I mean is there are Lie groups that are acting on parameter space that leave the function invariant, leave the actual function invariant. And it would be nice to understand these Lie groups. And moreover, depending on the data and depending on the parameter, the dimension of that group will change. And we can and should understand that. Okay. So here again, please don't, this is really a cartoon, but at least gives the idea of what I'm trying to say, that here's your parameter space, and if you identify points in parameter space that actually give rise to the same function, then the quotient will have different dimensions in different spots. And I believe that noisy data should spend more time stuck in regions of parameter space with higher dimensional redundancy. So the idea there is that, yeah, if you have sort of the true gradient, if you're always going in the direction of the true gradient, then you'll always sort of go along, you'll always change your function. But if you have noisy data, then you're going to start stepping in directions that are not really in the true gradient. And so you'll get stuck in these lower dimensional spaces because you're kind of popping around in here. Okay. All right, so let me now focus on a particular modern parameterized function class that I know a lot about the geometry of, and that is feed-forward ReLU networks. And I'm going to define actually two local notions of complexity in this talk. And this is the first and the easiest to measure and the easiest to understand. So I'm going to start here. Okay, so feed-forward ReLU neural networks. Probably I don't need to explain this, but I will. I'll go quickly. So this is a class that has this compositional structure. You map your input space to your output space by mapping through a bunch of hidden layers. And the form of the map is fixed. So, this is the architecture of the network. And each of these maps is an affine linear map composed with a component-wise activation function, as usual. And the activation function that I'm going to be interested in is ReLU. Mostly because the geometry and the combinatorics is just really, really beautiful for this activation function. Okay, so one of the first theorems in this subject, which is interesting and useful to know, is that if you allow yourself to vary the depth and the size of these hidden layers, you can achieve any continuous piecewise linear function with finitely many pieces. Okay, so this is somehow filling out that whole space of continuous piecewise linear functions with finitely many pieces. The other thing that I'll want you to know, I kind of like thinking about parameterized function classes, treating my input space and my parameter space as sort of on equal footing. And then the pair of them maps to the output space. And the other thing that I want you to know is that this function class is piecewise polynomial in the inputs and the parameters. Okay, so parameter space symmetries. So my claim is that you have this parameter space for this architecture, and you have the function space for the architecture, which is sitting inside of, you could think of as sitting inside of continuous functions from your input space to your output space. And I claim that this is not the same thing. Yeah, these are not the same. So there's a realization map. So as I described, if you identify parameters that give rise to the same function, then this gives this realization map. And the claim is that this is not injective. So there are many, many parameters mapping to the same function. And moreover, it's not like a discrete redundancy. It's a positive dimensional redundancy. And you can think of it as coming from, well, at least part of this redundancy you can understand as coming from a Lie group action on parameter space. Okay, so I'm actually not going to say much about parameter space symmetries because I couldn't fit it into this talk, but this is a really pretty story, and I'd be happy to tell anybody more about it if you're interested. What I really want to do is motivate kind of a nice number that you can associate to a parameter in parameter space, and this is a local notion of complexity, and it's related to this parameter space symmetry. So like I said, it's a local notion of complexity related to a parameter, not to the whole space, and I have to describe it first on a batch of points, and then I'll tell you what it is that's invariant of the batch. So if you have a parameter, then this gives you a function from your input space to your, I guess, by the way, I'm sort of, for simplicity now, I'm making my output space be one-dimensional, but it's not really important. Okay, so now if you fix a batch of points in your domain, what you can ask is, what's the subspace of the tangent space at this parameter that you can move via gradient descent on this batch? Okay, so it's the span of directions in which we can perturb near this parameter to change the value of the function just on this batch of points. Formally, so you let this batch of points define an evaluation map. So if there are m points, then you get m outputs for this fixed parameter. And this defines, and now you can take the gradient of this evaluation map on this batch. And this is, you have this Jacobian matrix evaluated at theta naught. And the rank of this Jacobian matrix is exactly that dimension that we're interested in. And this is what we call the batch functional dimension at this parameter on the batch. And to make it invariant of the batch, we do the kind of stupid thing where you take the supremum over all finite batches. Okay, but we also have a construction for a decisive batch that actually realizes this supremum. So it's not like you're searching everywhere. Okay, so I just want to note that that this is closely related to two things that probably people in this room have either worked on or care about, and that is the so-called neuromanifold. I already kind of described it. So there are a lot of people that are interested in looking at this realization map inside of this infinite dimensional space and using algebraic optimization methods there to kind of understand what's going on. And you can think of this evaluation map that I just described as like an empirical version of that. So rather than looking at your image in this infinite dimensional space, you just choose some finite dimensional space in which you can at least understand it partially. And the batch functional dimension is the local dimension of the image here. And similarly, the neural tangent kernel. So the idea here for kernel methods is that you are trying to construct some sort of inner product on your space by mapping your space, your input space, into some other Hilbert space that has an inner product in it and pulling that back. And in the case of the neural tangent kernel, that Hilbert space is just the tangent space at a parameter. So you have a different neural tangent kernel for each parameter in your space. And now this is kind of like an empirical version of that. So the batch functional dimension would be the rank of this empirical neural tangent kernel. So yeah, I think typically you think of the neural tangent kernel as the sort of covariance matrix there. So it would be JEZ times JEZ transpose. So you're looking at the pairwise dot products of these gradient vectors. But the rank would be the same for that as it is for the original Jacobian. Any questions so far? Yeah?
Just for clarification, so this is in the underparameterized case, right?
No, this is all defined regardless. I mean...
But the rank of the Jacobian defines the direction of descent in parameter space when the dimension of the parameter space is the maximal rank of the Jacobian.
Wait, sorry, say that again?
The rank of the Jacobian defines the dimension of possible gradient descent. If the maximal possible rank of the Jacobian is the dimension of the parameter space.
I don't think so. Maybe I'm not understanding what you're saying. All I'm saying here is that the rank of this matrix is the same as the rank of it times its transpose. Okay, let me show you some experiments. So these are some experiments that appeared in a paper, an ICML paper with Kathryn Lindsey and David Rolnick. And here we're just measuring the batch functional dimension for a very, very large batch for different depths and widths. So width 5, 10, 15, depth 3, 4, 5, 6. And what you can see is that this batch functional dimension, which should be close to the functional dimension, but we can't guarantee it. It's too computationally costly to choose our points specifically. But the point is, if you take a large number of points, you hopefully are close. Yeah, there's a big spread. So this slide is supposed to convince you that this functional dimension is inhomogeneous, especially for high depth. It's less inhomogeneous for low depth.
So let me make sure I understand what you
Yeah.
mean. So the width is the...
Yeah, the
the
dimensions
width
of the hidden layers,
okay.
and the depth is the number of hidden layers. Okay, so this is at initialization. you get quite a large spread of functional dimension. And now here are some kind of toy experiments. And I should say these are like really first experiments. So please don't, yeah, this hasn't appeared anywhere. But, and also we haven't run a lot of experiments. But I thought it would be nice to show you something about what happens during training. So here we have these three functions of increasing complexity. Blue is least complex, green is most complex. And these are just like, you just add in some extra sign functions with a period that's a multiple of your original sign function. And then we just sampled some data points with some noise, some Gaussian noise. And then we trained, and we measured the functional dimension. So, okay, so the first thing that I want to point out here is that, okay, so as you can see, so blue is least complex, green is most complex. So we trained for 1,000 epochs, and this is the architecture. So it's a pretty over-parameterized architecture. And what you can see, first of all, is that the functional dimension is roughly tracking the complexity of the function, at least the average. So this is a bunch of training runs, and we averaged the functional dimension by epoch. The other thing that I want to point out that may not be obvious until I point it out is that this initial functional dimension, you know, before you start training, is really surprisingly low. So the dimension of the matrix, that Jacobian matrix, is the number of parameters times the number of points, by the number of points. So it's 100 by roughly 1,000, but its rank is 15, roughly, at the start. So we really are starting with very, very low functional dimension at initialization, much lower than you might expect.
That probably depends on the particular initialization.
Yeah, it obviously will depend on the initialization. I mean, we saw that there's this spread. But the point is that it's far to the left of kind of what you might expect.
What are F1, F2, F3 here?
Right. It was those sine functions. This was just one period of sine, and then a little bit more complex and a little bit more than that. And here's sort of the learned functions for a single training run here. And yeah, this first line that's really far off, that's the sort of initialized thing. And you can see it's pretty low complexity. But I mean, the main takeaway I want you to have is that, yeah, say for this noisy data on this most complex function, it's really kind of underfitting, not overfitting. I mean, maybe we didn't run it for long enough. This is why I don't want to take too much out of these, but I did want to show you something. Okay. So let me just say some takeaways from what I just said. Functional dimension interacts with gradient-based optimization in a way that suggests that it tracks function complexity. It's inhomogeneous for this particular parameterized function class. And the thing that I want to talk about for the rest of the talk is to try to connect this dimensional complexity, this functional dimension, to something that we might care about if we're interested in generalization. Yeah.
So which cost function did you use?
It's just MSE, mean squared error.
Sorry, how were the data points labeled?
How were they labeled?
Yeah, like were they random? Like you said, you have 1,000 training points, right?
100, yeah.
Sorry, 100.
Yeah. I mean, we just sampled them uniformly. I mean, in fact, I think we just split the interval into 100 and just sampled them like that. And then the labels were just the function, but with a little bit of Gaussian noise.
Oh, okay. I mean, did you try, these?
Probably not.
Okay.
But yeah, keep going.
Okay.
Yeah, I mean, these are really just like very first experiments, like we did this last week. because
Oh,
I
okay.
was coming here. Okay. Okay. Okay, so what I'd like to talk about next is functional dimension related to some classical measures of generalization? And actually, this is a point where I'm going to start to get more technical, so I may lose your attention. So this is the right time to ask me questions about anything I've said so far.
So it's very interesting set of experiments. Have you thought about, say, doing the same type of experiments for ResNet, and look at the dimension?
It's a really good question, and I think ResNets will be less inhomogeneous in terms of
and that's
this
probably
dimensional.
The main reason they're
Exactly.
better trainable,
Yeah.
or more trainable.
Yes. I think you're right. Yeah. So yeah.
I have a question.
Mhm.
So, just to check my understanding, so this is a regression task, not classification.
It's a regression task, yeah.
And my second question is the initialization is Gaussian. Like before you change the network, you initialize the weight by sampling from a Gaussian.
Yeah. It's sort of the standard initialization, the head initialization, I guess.
Then why the rank of the matrix is very small? Because if you sample a random matrix, then I could imagine they have full rank.
Oh, yeah. Okay, you're thinking about the weight and bias matrices, which of course should have full rank. I'm talking about the
Jacobian.
this Jacobian matrix, yeah. Okay, so now I'd like to relate this dimensional complexity to a new local complexity measure that's a variant of VC dimension, and try to understand what the relationship is between these two local complexity measures. And so the TLDR answer to this question is no. We don't yet know how to prove that it's related to generalization, but at least I'm going to try. My job now is to describe this other local complexity measure that's a variant of VC dimension, and try to at least give you a picture that will help you understand why they should be related. Okay, so VC dimension. So again, probably everybody in this audience knows this, but let me just say. So this is a classical measure of complexity for an entire function class, and the idea is to look at how well you can do binary classification on using the class on finite samples of points. So the point is, if you're given a collection of m points in your input space, how many possible sign assignments can you achieve using functions in your class? So in this case, you can achieve all 2 to the 3rd possible sign assignments. And so you say that these points are shattered by the class, and the VC dimension is the maximal size of a shattered set. Okay. And this is all part of this PAC learning framework. It gives an estimate on the number of points needed to almost surely output an accurate hypothesis. But it's a global measure of capacity. So it doesn't capture any local inhomogeneity in the capacity, in the complexity. Okay, so I'm going to try to relate a functional dimension to this sort of variant of VC dimension called the pseudodimension. And the idea is now to do binary classification, but with respect to a fixed function that's not just the 0 function. So the idea here is that you kind of fix this function, and now you ask for your class how many sign assignments can you achieve via differences with this function, with this fixed function. And you play the same game. You say that a set of points is pseudo-shattered if you can achieve all possible 2 to the m sign assignments. And then the pseudo dimension is the maximal size of a pseudo-shattered set. Okay, and same sort of thing. It gives you some generalization guarantees that are similar to the VC dimension. Okay, so how are these ideas related to the functional dimension? So to understand this, I need to just tell you a little bit more about how I'm thinking geometrically here. So if you have a parameterized function class and you fix a parameter, then that gives you a function from your input space to your output space. And similar, yeah, and in the case of ReLU networks, this function is piecewise linear on the domain. Now, there's a sort of parallel story where if you fix a point, then this gives a map from your parameter space to your output space. These are these evaluation maps that I was describing before. And in this case, these are piecewise polynomial for ReLU networks. And so there's this really nice parallel between what we see for the decomposition of a domain for a ReLU class into these linear regions, and the decomposition of parameter space into regions. And again, please don't take this cartoon seriously. This is the idea here is that each point defines each point in your input space defines a set of it defines some piecewise polynomial, piecewise algebraic set. And the regions in the complement are the sort of semi-algebraic complex.
Sorry, shouldn't a ReLU network, doesn't it correspond to just a hyperplane arrangement?
So if you, no, not just a hyperplane arrangement. So, so here, if you fix a parameter, then you have a bunch of hyperplane arrangements for each layer.
Mm-hmm.
If you pull those back, you get what in the literature is called a bent hyperplane arrangement. This is what gives you your decomposition of your domain into these polyhedral sets. So these intersections of finitely many linear inequalities. But now, if you turn the story around and you instead fix points and you look in parameter space, these are now zero sets of polynomials, piecewise polynomials. Okay.
It's a multilinear function, piecewise multilinear.
Piecewise multilinear.
I mean,
So in the parameters, it's a polynomial. It's a polynomial in the parameters. Yeah. Okay. So so what I want to point out here, these are the zero sets. So if you fix a parameter in parameter space, and you now think of the parameter space as the difference class with that parameter. So now you're just with the function defined by that parameter. So think of that pseudo dimension graph or pseudo dimension slide. Basically now you're just comparing every function to that function. You're just taking the difference with that. And now you have these zero sets that are corresponding to the set of parameters for which evaluation at that point is equal to evaluation at that point for this fixed parameter. So this is defining some zero set of a piecewise polynomial, piecewise polynomial zero set. And so if you take the union of these, this is a piecewise algebraic set. And by algebraic set, I just mean the zero set of finitely many polynomials. Okay, and here's again a cartoon of what this might look like. Here's a particular parameter, and here are these two zero sets of the difference class with that parameter. And what I want to point out is that if you look in a neighborhood of this point, that this, this batch functional dimension on this batch should be related to the number of sign patterns we see. So the point is that these are exactly the cutoffs between where the sign is positive and negative for these various points. And so this local heuristic, this batch functional dimension, that's the number of linearly independent normal vectors. So think about linearizing right here. It's, you know, it's curved globally, but if you linearize, what you have is a hyperplane arrangement in the tangent space. And so this number of linearly independent normal vectors should roughly be log base 2 of the local number of sign patterns of the difference class. Well, up to a point, up to the dimension of the ambient space when the max number of sign patterns will begin to grow polynomially. So if you've studied hyperplane arrangements for very long, one of the first things you'll learn is that take an n-dimensional space. Now you can take n generic hyperplanes, or up to n generic hyperplanes. Each one will cut each of the previous regions into 2. But once you get past n and you start introducing more hyperplanes, all of a sudden you're not growing exponentially anymore, you're growing polynomially. So this is Zaslavsky's theorem. It follows from some classical results in hyperplane arrangements. Okay, but this cartoon is giving you essentially the geometry of the definition of what we call the persistent pseudo-dimension. So the pseudo-dimension would be something about the number of sign patterns everywhere. The persistent pseudo-dimension is about just the number of sign patterns locally near this point. Okay, and now here's the boring slide where I actually define it. So the persistent binary capacity of this function class near a parameter on a batch C, well, you're looking at a sufficiently small ball so that the number of sign patterns is no longer dropping. It's consistent. And then if you don't want dependence on the batch, then you just look at the max over batches of size m. So that's kind of allowing these local algebraic varieties to vary as long as you have m of them. And then we say that f has persistent pseudo-dimension m at theta naught if you're persistently pseudo-shattered, but for m points, m plus 1 points, you are not. Okay. And here's the theorem. For almost all parameters, in a way that we can make precise, the functional dimension of theta naught is less than or equal to the persistent pseudo-dimension of theta naught. And we conjecture that they're actually the same for ReLU networks.
Sorry, I missed, what was persistent again?
Persistent is that, yeah, I'll say in this picture. It's easiest to understand in this picture. In this picture, you might have a bunch of sign patterns everywhere. What we care about is the ones that are just near this point. And that's the persistent part. All right. Okay, so we conjecture that they're actually equal. And actually, this is there would be a lot of interesting math that would go into proving this conjecture. This statement is definitely not true if you don't say ReLU networks. If you just are looking at some piecewise polynomial class, for example, it's not necessarily true. Okay. And so the other thing that I want to point out is that lower bound was proved independently by another group that posted their paper before us. But that's okay, because I think it's the other bound that's actually really interesting. And so I'd like to say a little bit more about why we believe the other bound holds. But actually, let me pause for questions. Pause for more questions. Yeah.
So I just check my understanding. So the functional dimension is a rank of the Jacobian matrix.
Yeah, the sort of maximal rank.
That's
Yeah,
technical.
yeah, that's right, yeah. Okay. Okay, so I'm not going to be able to completely explain why we believe this conjecture is true, but what I want to do is explain to you why the conjecture is not obviously true with this example, and also explain a connection to some interesting mathematics, some interesting commutative algebra. So, okay. Here's an example of 3 zero sets that partition your space into 2 cubed regions. And what you'd notice is that if you choose another linear space, it's not going to be able to intersect each of your other spaces, each of these other regions. So with a linear space, you're not going to be able to cut this into 2 to the 4th regions. But with this guy, you can. So if you put this in here, it will actually separate each of your 2 cubed regions into 2. So you get 2 to the 4th regions. And here are the equations. So, and what you'll notice, these gradient vectors are the normals to these coordinate hyperplanes. And then this last is the sort of, well, it's the gradient vector, but now considered as a function of theta 1, theta 2, and theta 3. And now, one of the things that you might notice about this algebraic Jacobian matrix, so now not evaluating it a parameter, but instead viewing it as a matrix over the full polynomial ring, is that its row rank over the polynomial ring is 3. So, namely, oops, what happened? Right. Its row rank over the polynomial ring is 3. Namely, you can realize this row as a linear combination of the first 3 rows if you allow yourself to work over the full polynomial ring. But its row rank over the real numbers is 4. And the claim is, actually, this is interesting. Oh, this is doing the thing. Oh, it worked. OK, great. Right, the claim is that this is interesting. So one of the things that Kathryn and I proved is that this rank gap actually captures the gap between the functional dimension and the persistent pseudo dimension. So what we proved is that if you have the persistent pseudo dimension on a batch, I'm going to state it in terms of batches, but this kind of works in the limit as well. If you look at the persistent pseudo dimension on a batch, it's bounded between the rank of this algebraic Jacobian matrix over the polynomial ring, the row rank, and the row rank with respect to R. And in fact, this is the functional dimension over here.
Can you find the row rank for 4 to make sense?
Yes, that's a weird thing about matrix algebra over rings. Actually, a fun fact is that if you work over like a general commutative ring and you take a matrix, its row rank might not be the same as its column rank, and it might not be the same as the determinantal rank. So this,
R, you say?
but over R you're fine. Yeah, over R you're fine. But the point is that you're now working over a polynomial ring. And yeah.
His row rank over R is 4.
Yeah, the row rank of this matrix over R, over the real numbers. Meaning if you're allowing yourself just to take linear combinations, but with real numbers, not with these polynomials. you can't realize this row as an R linear combination of these rows. You need to work over this larger polynomial ring. Okay, right, so point being, this is the functional dimension, and there's that lower bound that we're talking about. And in my last few minutes, I'll just explain why the row rank of this matrix over the real numbers is bounded below by something interesting, by another interesting matrix over the real numbers. And this is really where this conjecture comes from, that actually we believe that this is true as well. But this is hard, this would be hard to prove.
So for ReLU networks, these Jacobian matrices are they're multilinear, right?
Yeah, that's
So
what I'm
is that the structure? Do you think that, like, for sort of any any matrix whose entries depend multilinearly on theta, that you should have an equality between the
Maybe,
R?
yeah, I mean, maybe that's what, I mean, that'd be cool. Okay, let me just in my last few minutes tell you a little bit about the really interesting relationship between the sort of combinatorics of ReLU networks and these ideas that we're talking about. So, of course, we have the computational graph for the ReLU architecture. These red nodes here are representing the bias nodes. And the idea is that you can actually understand the polynomials in this piecewise polynomial structure by looking at paths in this graph, weighted paths in this graph. So if you label each edge by a parameter, so the black edges here are labeled with weights, the red edges are labeled with biases, then the polynomials are going to be sums of monomials associated to open paths. Maybe this is what you guys mean when you say multilinear. Yeah. Okay, yeah, then we're talking the same language. And the point is that, okay, so here's an example. Here are two of the monomials associated to this path and this path. And then they're kind of weighted by their inputs here. You weight the bias nodes with 1 always, and then here's the inputs, input coordinates. Okay, and now for ReLU networks, if a neuron is inactive at a point, meaning it's not on at that point, then the paths through that neuron disappear in the polynomial. So this just corresponds to monomials getting canceled or disappearing from the polynomial. And so now we have this very natural matrix, which is defined by this other group from Toulouse called the activation matrix. The rows are the data points, and the columns correspond to these paths. So there are quite a few columns. And we just populate this matrix with the input to the path if the path is open, and 0 if the path is closed for that point. And the claim is that actually the rank of this matrix is an upper bound for the real rank of that Jacobian matrix, the real row rank of the Jacobian matrix. And this is just an exercise in linear algebra, essentially, or linear algebra over a polynomial ring. But the point is that you can take this activation matrix and multiply it by a vector of the monomials, the appropriate monomials, and that's going to give you these evaluation maps. And so now if you have any kind of R linear dependence, this carries over. And it also carries over to the Jacobian because that's a linear operation as well. So this is what tells us that this rank of this R rank of the Jacobian, this algebraic Jacobian, which is an upper bound on the persistent pseudodimension, is also bounded above by the R rank of this activation matrix. And I just don't see any other ways to get, I just don't see any other ways to get relations. And maybe it's this multilinear structure. Anyway, I haven't thought hard enough about it, but maybe somebody else smarter will figure it out. So that's where the conjecture comes from. Okay, so let me just stop with some takeaways. So modern parameterized function classes, like feedforward ReLU networks, have inhomogeneous dimensional complexity, and this should impact the dynamics of learning via gradient-based optimization. And for ReLU network classes, I believe this local dimensional complexity should be equal to something that tracks generalization. And that's it.
Thanks, Ellie. Any questions? Juan.
Yeah, thanks for the talk. So I was just curious if, so if I do something that would be kind of presumably destroying the structure that you're building here, that would be replacing the value by the reality, you know.
Yeah,
the
right, something
software,
smooth.
right? So for all purposes, it's fair to say that there's nothing that's breaking in terms of generalization ability. You know, it seems like the number of parameters would be the same, the geometry would be, I would imagine, very similar.
Probably,
Yet,
yeah.
some of these things that you are computing would presumably be broken, right?
Yeah,
So
yeah,
how
I'm sure.
do you reconcile these two things? Like you know, how much would you be overfitting to the piecewise linear structure of values when maybe this is, you know, you could just get it, you know, remove it and still keep the basically the same essence.
Yeah, I see what you're saying. I mean, like, the short answer is I don't really know what happens when you smooth out ReLU, when you destroy this sort of, I mean, ReLU is a very kind of violent activation function. It's zeroing out a lot. So yeah, I don't know. Yeah, short answer is I don't know.
I had a continuation of this question. So if you had the, so as you said, like your functional dimension will completely break when you switch to like a smoother activation function.
Mm-hmm.
But would these local pseudo dimensions still stay approximately the same even if you switch to a smoother function? And would that suggest that these local pseudo dimensions are what we need to look at, not functional dimensions?
Oh, that's a really interesting question. I mean, you can compute local functional dimension and persistent pseudo dimension for anything.
Yeah,
Yeah, the question is about the inhomogeneity, though.
but the local function dimension will break down what
Mhm,
you consider
mhm.
any smooth thing.
Yeah.
It'll become the full rank, and
Right.
you'll get no information. But will the
Right.
persistent pseudo dimension still give you something useful at that point?
Yeah, probably. Yeah, I would hope so. I mean, okay, maybe a more fair answer to the question that you guys are asking is, I mean, okay, so here we're talking about rank, which is a very discrete notion, but there are kind of these fuzzier versions of rank, like stable rank, and you know, you could be very close to a lower rank matrix without actually your rank collapsing, and probably have a lot of the same behavior. That's something that I haven't really explored, but it seems like a reasonable thing to explore for the case of these smoothings of ReLU.
Go ahead.
Okay, another question related. So how does the role of the architecture, so here like the depth and the width hasn't been explicit, right, in this computation? Where do you, for a practitioner, for example, where does how can you extract back how the choice of architecture will influence this notion of complexity?
Yeah, that's a great question. That's a great question. I mean, all we know is the empirics, which is that for deeper networks, there seems to be more variation at least in the functional dimension. And we don't really fully understand that beyond, I mean, yeah, somehow this came up in Thomas's talk, and also, I can't remember, I think your talk as well, that, yeah, Richard's talk as well, that that there is this sort of collapsing that seems to be happening in deep networks that, yeah, coming from, yeah, you could think of it as pulling back these truncation maps, and then everything sort of, this these blobs are kind of collapsing to lower dimensional objects. And I would imagine that implies that some explicit relationship could be made with what happens to the functional dimension because of that.
Okay, let's thank Ellie again.